So in the previous example, we used a Riemann sum with midpoints. So we call that a midpoint Riemann sum to estimate the area under a curve over some specific interval. We're going to do a similar problem. It's a different function this time, and we're going to do it over the interval 2 to 10, and we're going to use only 4 subintervals this time, all of equal width, which is usually an assumption that we're making, but we're going to try each of the 3 different types of Riemann sums that we've talked about: right hand, left hand, and midpoint. Okay, so to begin with, let's work out, let's see. Oh yeah, let's do the right hand Riemann sum. So the first thing I'm going to do, this will apply to all 3 of those, is find delta x. Remember, that's b minus a, so 10 minus 2, over the number of subintervals we're cutting this into, which is 4. So that's 8 over 4, or 2. Okay? Now, in the previous example, I wrote out the summation notation. I'm not going to use that summation notation here. I'm just going to go straight to like the sum. But just know that we could do that if you want the notation in there. So for this right-hand Riemann sum, I know that I'm plugging the right endpoints of my subintervals into this function, but I haven't determined what those right endpoints are. Rather than list them out, I'm going to do a little picture. This is going to represent just the x-axis. If I wanted to do this problem like I did the previous one, I would sketch the curve, so I'd need an x-axis, a y-axis, the curve, and all of these rectangles. You don't actually need all of this stuff. It helps you to see what's going on, but once you've done this a few times, what really matters is what's happening on the x-axis here. So we're taking 2 to 10, and we are cutting it up into 4 subintervals. Each one will have a width of 2. So start at that 2 and then count by 2s. 4, 6, 8. Okay, so 1, 2, 3, 4. Those are the 4 subintervals I would have cut this interval from 2 to 10 into. And if I were to sketch the whole picture, we would be putting rectangles on top of these, right? But knowing that I'm using a right-hand Riemann sum, I know that I'm only using these right endpoints when I plug them into my function. So what that means is that I'm going to plug 1, 2, 3, 4. I'm going to plug 4, 6, 8, and 10 into these functions, into this function here. And then I'm going to compute that using the Riemann sum thing. So as we saw in the previous example, each one of these f of 4, f of 6, f of 8, f of 10, I would be multiplying by delta x, which is 2. But because that 2 is going to appear in every term, we can preemptively factor it out. So 2 times f of 4 plus f of 6 plus f of 8 plus f of 10, right? Now, I'm going to skip a lot of the work here because I'm going to trust that you are able to plug numbers into a function and get a value for each one of these and then add them up and then multiply the whole thing by 2. I don't think it's worth the time to write out all of that work. It's more about knowing how to set this up. So once you have done this, you would find that this right-hand Riemann sum is going to give me an approximation of, where did I put it? Oh, it's 8. Or sorry, 80, not 8. Okay? This would work out to 80. Verify that though. Try it on your own. Make sure that that actually is correct. What about B? For part B, I would be using left endpoints. So here are the left endpoints of those intervals. 2, 4, 6, 8. Delta x will be 2 still. Nothing has changed about the widths of those intervals. It's just which endpoint I'm using when I plug it into my function. So that's going to give me 2, again, times. Now we start with f of 2. And then we count by 2's. F of 4 plus f of 6 plus f of 8. We stop there because that is the last of the left endpoints. This, interestingly enough, also comes out to 80. It's somewhat of a coincidence, but if you're looking at that and you're trying to reconcile it with the fact that right endpoints have given us overestimates, whereas left endpoints have given us underestimates. That's not universally the case. It depends on what the function is. So consider this for a second. This is like off to the side. If I have a function that looks like this is an increasing function. And if I'm using right endpoints, then I will always have overestimates. And we've also seen that left endpoints give us underestimates, right? What if the function is decreasing, though? What if I have a function like this? Well, now, look at what happens. If I use right endpoints this time, suddenly I have underestimates, right? So it's not just about whether it's a right endpoint or a left endpoint. It's about whether the function that we're using it on, oh, I drew that off screen. It's about whether the function we're using it on is an increasing function or a decreasing function. Because in this case, left endpoints would actually give me overestimates instead of underestimates. It flipped. If the function is neither increasing nor decreasing, but maybe it does both at different points, like a parabola, which the graph of this thing would be a parabola, then if we do a left and right endpoint method, notice the left endpoint, I'm starting with some overestimates, but then I switch to underestimates here. And then my right endpoint method would start by giving me underestimates, but then it would give me an overestimate here. So we're going to see a balance between those two things, and that's the reason why we can end up with our left and right hand Riemann sums giving us the same value. That does not mean that the actual area under that curve is 80. It just means that we're looking at something kind of like this. In fact, the midpoint rule, or the midpoint Riemann sum, is, we know it's generally more accurate when it gives us an approximation for that area, and it's going to give us something different. So if we use midpoints, notice my midpoints are 3, 5, 7, 9. Those are the values I'm plugging in to my function now. 2 times f of 3 plus f of 5 plus f of 7 plus f of 9. And again, I'm not going to go through all of the work of actually showing what this looks like when I plug it into that function. I'm going to let you work that out. This one comes out to 88. So it turns out that our midpoint, which is usually more accurate, gives us a different value. Okay? All right. We're going to do several examples like what we've just done, but looking at, the problem from different angles. So what if I don't have a rule defining my function? What if I don't know that y is equal to something like 2x squared plus 20x minus 5 or something like that? Sometimes I'm only given a graph with some of the points indicated on that graph. So down here, we want to estimate the area under the curve on the interval from 0 to 6 using a right-hand Riemann sum with 6 subintervals. Well, notice in this case, the delta x, we're using the interval 0 to 6. That would be 6 minus 0. And we're cutting that up into 6 subintervals, so dividing it by 6. In this case, delta x would equal 1. So the width of each of these subintervals is 1, and we're using the right endpoint of each one. So that means my subintervals are going to be from 0 to 1, then 1 to 2, then 2 to 3, and so on until we get to 5, 6. Using only the right endpoints, we're going to get these rectangles here. And again, you don't actually have to draw these, but especially when you're getting used to this method, it's a good idea to do it just for the sake of understanding what it is you're doing. Okay? So now that we have kind of sketched this out a little bit, notice the right endpoints are 1, 2, 3, 4, 5, and 6. So that means that my Riemann sum, my right-hand Riemann sum is delta x, which remember we've been preemptively factoring that out. Sorry, I felt like I have to sneeze. Nope, it's gone. Okay, we're going to take that 1, factor it out. There it is. All right, which is not really going to do anything, but just so we don't, think when we look back at this later that we forgot to deal with the delta x. I'm going to write the 1 there in the first step. And then we're going to add up f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. Use square brackets there. Okay. Now the 1, I'm going to get rid of it in the next step because I know that multiplying by 1 won't change anything. But where do I get f of 1, f of 2, f of 3 and stuff from? Well, these would be the y coordinates of the points whose x coordinates are 1, 2, 3, 4, and so on. And those y coordinates are indicated to me here in these ordered pairs. So I know what they are. It's 21 plus 22 plus 15 plus, that's a 6 right there, plus 1 plus 6. Okay, that one is easy enough to work out by hand if you want to, or in a calculator. It comes out to 71. So that would be my estimate for the area here using right endpoints. Notice that this curve is not increasing or decreasing the entire time over that interval. So when I use my right endpoints, sometimes I get overestimates, other times I get underestimates. That's kind of what we were seeing in the previous example. Let's try another example. So here it says given below is a table of some particular values of f of x. We want to estimate the area under the curve y equals f of x on the interval from -3 to -0.5 using a left-hand Riemann sum with 5 subintervals. So we technically don't need to draw this because the table gives us the information that we need. But again, you might be struggling to visualize what's happening here while you're figuring this out. So we're going from -3 to -0.5. We're using 5 subintervals on that interval there. So to find delta x, that would be the right endpoint, -0.5 minus -3 over 5. So when you do this subtraction here, -0.5 minus -3, as the thing is plus 3, that's 2.5, divided by 5 is 0.5. So we count by 0.5s. That would take me to -2.5. Then -2, -1.5, -1, and notice I have 1, 2, 3, 4, 5 subintervals all together. Okay, we want to use left-hand Riemann sums, which means I choose the left endpoint of each one of these subintervals to then plug into my function. So delta x, preemptively factor that out, that's 0.5, times f of -3 plus f of -2.5 plus f of -2 plus f of -1.5 plus f of -1. See how I used only those circled left endpoints here. How do we get these values? Well, we are told in the table what each one of these is equal to. We're told that f of -3, for example, is 2.3. And that f of -2.5 is 7.1. And you notice I'm just using all of these values except for the 2. So that would be plus 9, plus 1.4, plus 1. 1, 2, 3, 4, 5. 1 for each rectangle that we would be constructing there. Okay? This, again, plug it into a calculator, try to do it by hand. Either way is actually fine, and it's not hard to do this one by hand either. This comes out to 10.4. So that's my estimate for the area there. Okay? So as you can see, there's a bunch of different ways of approaching a problem like this depending on what information you're given about your function. It can come in the form of a table, you can be given a graph from the beginning, you can be given some algebraic rule that defines the function. We've seen all of those now. And it's at this point that we want to start looking at why we care about the area under a curve. Even though this is a calculus for business and economics class, we're going to use a physics example to start. This is the classic example that we look at to make sense of both the rate of change problem when we deal with derivatives, as well as the area under a curve problem in this chapter. So velocity and distance traveled, we're looking for a relationship there. Okay. Now, we know, hopefully you know, that if you are in a car or looking at some kind of moving object, and you happen to know that it's traveling at a constant velocity. Remember, velocity, you can kind of think of that as the same thing as speed. The only difference is that velocity can be either positive or negative depending on which direction you're traveling. But aside from that, you can think of it like speed. The distance that an object travels is equal to its speed or its velocity times the amount of time it's been traveling. So if you're going 60 miles per hour and you travel for 3 hours, 60 times 3 is 180. You've traveled 180 miles. Right? However, generally speaking, velocity is not usually constant. Usually you speed up and you slow down over the course of time. And so this is not a reliable formula to work with over long intervals of time. So, however, it does provide us with a means of approximating the amount of distance traveled, even if velocity is changing. So we're going to think about it this way. Suppose that you're using the odometer on your car is broken, and you're trying to estimate the amount of distance that you've driven over the course of a 30-second time interval. Okay, the way we're going to do this is the odometer is the thing that tells you how many miles you have traveled, but that's broken. You can't use that. Your speedometer, we're going to assume, is working, and so you can see how fast you're going at different intervals. You record that data here. So you start with a speed of 17 miles per hour, and then 5 seconds later, you're traveling at 21 miles per hour. Then another 5 seconds later, so 10 seconds after starting, you're at 24 miles per hour, and we have all of these other readings, all the way up to 30 seconds broken up into 5-second intervals. Okay? Now, even though your velocity has sped up from here to here, so you are going faster now than you were then, it's a small change over a small amount of time. Velocity is generally going to be a continuous function, because continuous functions mean small changes in your inputs produce relatively small changes in your outputs. You don't have jumps or discontinuities or things going on like that. So in order to make this problem a little bit more manageable, we're going to convert this table from miles per hours into feet per second. I'm not going to show the conversions here. We're just going to show it. We're going to give you the table, and you can trust that these speeds in feet per second are the same as these speeds in miles per hour. But if my velocity or speed is not changing a whole lot over the course of this small little subinterval, then we can just approximate the speed over each subinterval by a constant. So that constant can be chosen in a bunch of different ways. You can either choose the left endpoint of that subinterval or the right endpoint. So for example, I want to approximate the distance that I've traveled for the first 5 seconds. Now I know that my speed was not 25 feet per second the entire time, but because the speed doesn't change a whole lot from 25 feet per second over the course of that interval, let's approximate the speed and just assume that we were traveling at a constant speed of 25 feet per second for the first 5 seconds. So that way, because it's constant, I can use this formula. I can say the distance traveled was approximately my speed, 25 feet per second, times the time, 5 seconds, so about 125 feet. I've gone about 100, I was off screen. I've gone about 125 feet. Then if I want to approximate how far I've traveled over the next 5 seconds, I'm looking at this interval here in my time, so 5 to 10 seconds. I went from 31 feet per second to 35 feet per second. I don't know if I sped up that whole time, if I sped up and then slowed down, or I'm not really sure what happened. But we're going to use the left endpoint of this subinterval here to determine, to approximate our velocity as being constant. So I'm going to assume my velocity was just 31 feet per second over that entire 5 seconds. Then I use that same formula, speed times time, 31 feet per second times the 5 seconds in that interval would be about 155 feet, okay? I can keep doing that. I can keep approximating my velocity over each one of these subintervals using a constant, and in this case, I'm using the left endpoints as my constants, multiplying it to the interval in my time and getting a distance as a result. Then if I add up all of those distances, I would get an approximation for the total distance traveled over that 30-second time interval. Okay. I could have done the same thing using right endpoints as well. I could have used 31 times 5 for the first interval instead of 25 times 5. But notice that 5-second interval that's happening here is like your delta x. I would actually call it delta t here since we're talking about time. 5 seconds, right? So really what I'm doing is I have a function that depends on time. So I can think of velocity as a function of time, v of t, for example. And I'm taking my delta t, the change in that the width of those subintervals, times v of t at a particular value of t in each one of these subintervals. So for example, v of 0 is 25, v of 5 is 31, and I'm multiplying them. Just the same way I did when I'm finding the area of these rectangles. So what that tells me is that rectangular approximation method that I was using up until this point can be interpreted as a problem that, or can be interpreted as a distance traveled using velocity as the curve. Okay? Here. Now, again, this is a calculus for business and economics class, so we're not looking at physics examples. We're not taking velocities and distances and all of that kind of stuff. What we are doing, though, is we are looking at rates of change in other contexts. And velocity is just a rate of change in the distance traveled by some object. Technically, we would use the word displacement because displacement allows for that distance to be measured in terms of positive or negative, depending on the direction traveled. But the point is that velocity is a rate of change. Generally speaking, rates of change are represented by derivatives. So what that means is that we can interpret this area under a curve thing as the net change in a quantity that's given by a function f of x if the curve that we found the area beneath is the graph of its derivative. So in other words, if you have a function f of x, you take its derivative, f prime of x, that's its own function, so it has its own graph, but then you find the area beneath that curve over some interval. What that's telling you is the net change in the original function over that interval. How much did that function increase or decrease by over that interval? Okay. Now, it's important to note that when we do this, the units of measure change. So going back to my velocity example, I'm going to write this off to the side. Distance, or let's do the right-hand side. Velocity, in this case, we measured in feet per second. Time is measured in just seconds. And distance is measured in feet. So if I'm just looking at the units, notice that the velocity looks like a fraction, and the thing I'm multiplying it by has the units that correspond to the denominator of that fraction. When they cancel, it gives me that feet right there. That's going to happen anytime we're using a function that can be interpreted as a rate of change. So for example, in this example here, we're given units for x and f of x, where f is some positive function, and we want to determine the appropriate units that we would use for the area of the graph. So that's like distance from a velocity graph, the example we just talked about. So here, if the units for x are pancakes and the units for f of x are dollars per pancake, then what are the units of the area here? So that in this case, I'm looking at dollars per pancake times the units for x, pancakes. These cancel, and I'm just looking at dollars now. Okay, so what this would tell us is, for example, if you had some function that represented the amount of money that you make for every pancake that you, or for selling X pancakes, right? And you find the area under that curve from A to B. So over some interval from A to B. Let's say A to B, that's like 10 to 20, right? Then the area under that curve would represent the total amount of money you made between selling 10 pancakes up to 20 pancakes. So after you've sold that 10th one, you start counting the amount of money that you make up until the 20th one. That area will give you that amount of money. That's what we've kind of just worked through here. B, what about this? If the units for f of x are pounds and the units for x are feet, then what are the units of measure here? So this time the units for f of x do not look like a rate. There's no per in there. So it's just pounds times feet. And we actually call this pound feet. This actually has a name. It's a unit of force that's used in physics a lot. Okay? What about this one here? C, fortnights times cubits per fortnight. Notice there's a second per in there. Per fortnight. Well, this cancels with only one of these, and what I get are cubits per fortnight. When would we ever use a unit like that? I have no idea, but that's not really the point. The point is understanding how to determine the units that our area is measured in, dependent on what we measure x and f of x in. Okay? That's going to be it for this part.